Okay, let us start this. So I think we went till over here, isn't it? And we found out how to apply the conditions of Ampere circuital law, isn't it? Yes. Let me give you one more part, one more type of that. Let's suppose if I have a wire carrying current I, okay, and if the empirical loop is like this way, sorry, void or not. So this is my empirical loop. So I told you that many people will think that sir empirical loop is symmetrical always, but the answer is no. Empirical loop can be symmetrical, cannot be symmetrical also. Are you able to get me or not? But it has to be, yes, it has to be closed empirical loop. Void or not. So question is then write the Ampere's law equation. Can you write it? Write it fast. Yes, just like we write now over here for this, that sir, there were how many currents that were passing? Almost I1. Here, there were one, two, three, four. So there were two currents going up, two currents going down. So we wrote this equation. Then for here, we wrote I2 minus I1 and I3 and all. Are you able to get me or not? Here also we wrote 3 mu I, and so this equation I want you to write. So look over here. Basically, if current goes like this way, so it will be kind of clockwise kind of magnetic field will be generated, isn't it? Are you able to get me? So now look over here. If you see that basically in one closed loop, this can be treated as a one closed loop or not. Only one current is passing. Now how much is that? I. But in reality, if you look over here, how many closed loops are there? One, two, three, 4, and 5. Are you able to get me or not? Is it clear? So there are total how many closed loops? 5 closed loop. But what if, see, these are formed over here, but there is one big external closed loop or not? So there are how many? 6. Are you able to get me or not? Okay, so therefore I'll write the equation as integral b dot dl vector is equal to simply 6 mu naught I. Is that clear or not? So remember, you count the number of closed loops, these closings, and then the total big is also a kind of magnetic field generation loop or not. So that's why total number of loop is how much? 6 may not. Are you able to get me or not? This is clear? Okay. Yeah, right. Then I'll give you one more problem. Okay. Got it? Okay. So question is very simple. That this is my loop this time. Okay. This kind of a formation. Current I1 enters towards this side. Current I2 enters over here only. And I2 comes out, and then there is I3. So see, I1 goes like this way. This was my current I1. Are you able to get me or not? I2 goes like this way. Okay. And I3 goes like this way. Know it or not? This is I1, I2, I3. Question is write the Ampere's law equation. Question is write the Ampere's law equation. No. Can I help? See, basically first I need, this is my empirical loop, isn't it? This black line is a empirical loop. So I need to consider the direction of a magnetic field or not. Let's suppose this is like this way. Now, in the, if it is in this direction, then we know that perpendicular components are positive of it, isn't it? If you look over here, so it is anti-clockwise. So it means that perpendicular like this way, and here also perpendicular like this way. These are positive, isn't it? So yeah, I suppose it because I do not know which current magnitude is maximum. So then it is. We can, so see, if you consider, you can consider clockwise also, no problem. But then if I consider clockwise, then the current downwards are positive. Are you able to get me or not? So mu naught. See, in the first loop, there are two currents. I1, then I2 comes. So I1 plus I2, isn't it? And in second loop, what is the equation? Second loop, I3 goes up. So I3 is, but I2 goes down inside it or not? So minus I2. So answer is integer. Is it clear? Clear or not? Okay. Yeah, I2. Yeah, going in and then going out. Okay. Can I give you one more question? Okay. Tell me. Yeah. Sorry. Yeah, correct. I1 plus I3. Yeah. Can I give you one more question? Now look over here. Uh, Okay. Now question is very simple, but yeah, let us see that. Saying that I have some kind of a closed loop, right or not? And in this, what is happening at the center of it? There is a very big current perpendicular to it. Are you able to get me or not? Yeah, yeah. Current is going inside. Okay. Word or not? Okay. Point is very simple. So look over it. I'll write the question. In the following, calculate the integral B dot dl. I'm not asking magnetic field. I'm calculating B dot dl for the path A, B, C. Are you able to get me? When a very long wire carries current I, when a very long wire carries current I and it is perpendicular to the plane of paper. Okay, so let's suppose I mark the points. This is A, this is B, and this is C. So find the magnetic field. Find the integral B dot dl for this ABC part. Are you able to get me or not? Yeah. If this is current I which passes through the center and perpendicular to it. Yes. Yeah. Tell me what will be the answer. This is not about infinity. I'm just asking you b dot dl. Basically, the formula of integral b dot dl is what? Integral b dot dl is mu naught into I enclosed. That's all. But that is for full closed loop. Already a constructed loop is there. This path integral b dot dl for this path it is asking. And this is basically a closed loop only or not? Are you able to get me? So see, this is my full closed loop. So here, as I'm saying that I want b dot dl for only A to B to C. So this is one fourth of the closed loop or not? So this implies integral b dot dl for path A, B, C is simply 1 by 4 mu naught I. That's all. That's your answer. Not closed loop. Do not use this integration. Write it simple integration. By symmetry, right or not? Is this clear? Okay, let us do one more question. Okay, just like earlier one only, but little bit change is there. Okay, this time I have the closed loop, but this time the current is passing through one of its edges. Right or not? I'm considering a perpendicular current, but it's passing over here. This over here, this is my perpendicular current I. Right or not? And then you have to find the cross. No problem, right? Regarding that dot or cross, same thing. It is perpendicular to the plane. My question is very simple. Once again, find the magnetic field. So, yeah, this is point A, this is point B, and this is point C this time. Once again, you do the find the integral B dot dl for part ABC. Tell me first. Mm-hmm. Yes. Think. What to do over here? Correct. Something you should do. Okay, should I help? See, I'll tell you, I'll give you one idea. Basically, this is not the arc which is visible to us, isn't it? See, this is at this point. So, with respect to C, can I construct one arc over here or not? And this angle will be exactly 45 degree, because at the two ends of the two diametrical ends always create 90 degree, and this is my center. So if I divide half, it is 90 basically. Are you able to get me or not? Is this clear? Confirm. So now look over here. Basically, I can create an arc over here or not in this fashion. Are you able to get me or not? Is it clear? Now, see, this point is D. Consider this point to be D. So, look over here. If I want to write the magnetic field to this, can I write the magnetic field to this or not? CD, let's call it as CDE. Okay. It subtends how much angle? 45. So, basically, and for this, if you look over here, this is radius R, this is radius R. So, the radius is root 2R or not? Clear? What is radius R? Root 2R. So, 4R CDE. Arc length is how much? It is R, yeah, R into theta, that is root 2R into, what will be that? Tell me. Theta is how much? 45 degree over here or not? Total is 90 degree or not? It's pi by 2. So that means you can consider basically it is equal to uh, R pi by root 2. Are you able to get me? Confirm? Now look over here, see. So the point is very, very great that when I calculate all these kind of things, when I try to find all of these things, they not only go through a simple calculation, but they involve some kind of a logical thinking also. Okay. Now you tell me one thing, as I calculated that this is something r pi by root 2. Now see, total angle of the circle is how much? 360 degree. This is how much? 90. That means it is 1/4 or not? Yes. So can I write the B dot dl equation for CDE? So CDE B dot dl is equal to mu naught I by 4. How much is that? No. Why I will use R pi? That is arc length. That is of no use. I'm just considering that, see, whole circle would have enclosed current I. So it would have been mu naught I. But for this length, how much current is enclosed? Only 1/4 is closed or not? So, so integral B dot dl for only part CD, only just part how much CD is how much? Mu naught I by 8 or not? Just this half part. Just this half part CD. Did to CDE it is 1 by 4. What? अरे बाबा, CDE के वजह से कितना है? म्यू नॉट I by 4 है ना? तो CD उसका हाफ है या नहीं है? तो 1 by 8 ही होगा ना, म्यू नॉट I by 8. Okay. So mean see, for this whole part we calculated that it is 1/4. For CD then it will be 1 by 8, isn't it? Because it is half of 1 by 4 mu naught I. Got it? Now look over here. So as I got to know about CD, I asked you find mu naught, find due to ABC. But I cannot write ABC because it will not close this circle current I in a perfect way. Are you able to get me or not? So I can itself consider this as an empirical loop over here or not. This is small reason. So integral closed loop A B C D A once again. B dot dl is mu naught I. But is there any kind of current inside it? No. So it is equal to 0 or not. But what is integral B dot dl A B C D E? It is nothing but integral A B C B dot dl plus integral C D B dot dl plus integral dA path B dot dl, and that is equal to how? 0. Now you see that dA lies along the line of I or not. So look over here. IDL means what? If you look over here, IDL is along J cap. Yes. And DA, this line is along some kind of I cap. And I dot J, B. So look over here. If I want to find integral B dot DL for DA path, so DL is along, look over here. If you look over here, then see that DL is along that J cap direction, isn't it? So let's consider minus J cap. Well, B vector will be on this loop. dA is also a loop, so I cap. So I dot minus J cap is how much? 0 or not? So this means that integral B dot dA for dO is how much? 0. So this term is 0. So therefore integral ABC B vector dot dl vector is minus integral B dot dl for CD. So this is, if I consider the magnitude of it, I just consider the magnitude, that integral ABC B dot dl is simply DC B dot dl. Can I write negative side if I change? So I consider the opposite one, DC. Are you able to get me from here to here? So that is what is still same, mu naught I by 8. It is mu naught I by 8. Dot cross, how come will be I cross J cap is K cap or not? How come it will be 0? It's cross. Here also it is cross only, no? Red is also a cross. It's a cross over here. Okay. Written. Can I move ahead? Okay. So right now we got to know about how to use the Ampere circuital law for the different current closed cases, isn't it? Now we'll consider Ampere circuital law for finding the magnetic field of the symmetrical objects. Are you able to get me or not? So first case, let us give the heading. That is, first is infinitely long wire. Infinitely or infinite, just write infinite long wire. Clear? Now let's suppose if I have an infinite long wire and I want to find the magnetic field due to it, okay? Like this. It carries some current I. Now, if I want to find the magnetic field, I need to first consider empirical loop or not. There should be a consideration of empirical loop, isn't it? So this is my empirical loop over here. Are you able to get me or not? Let me draw it perfectly. Okay. So this is my empirical loop or Amperian loop. Amperian. Oh, is it Amperian loop? Okay. Now this Amperian loop, if I just see into this Amperian loop in a plane, then it is a kind of a circular region or not. And in this, and current is going upwards away from the particular paper, isn't it? Now if I consider over here, let's suppose if I select some points, then here, see, if I consider the magnetic field is upwards, isn't it? Yes. But what is the direction of dl? Direction of dl is also along same direction or not? Yes. So look over here, this is dl. So here theta is how much? 0 degree. Similarly, if I select a point over here on topmost point, here also magnetic field is along this direction, and similarly dl is also along the same direction. So once again theta is how much? 0 degree. Are you able to get me or not? So everywhere over here, magnetic field and dl are in the same direction or not? Yes. So this means that basically if I can apply the integral of Ampere's law by Ampere's law, can I just apply integral B dot dl is equal to mu naught I enclosed. Yeah. Now look over here. This integral B dot dl, magnetic field is always same, isn't it? So B will come outside. And if this is a loop of radius r, so then dl means what? 2 pi r. Mu naught I enclosed is I. So any point means if I want to find the magnetic field at any point at a distance r from the wire, so then B is equal to how much? Mu naught I by 2 pi r. But for which kind? Yeah. Yes. Yes. We find out using Bart-Savart's law. Yeah. Is it clear? Clear. So now look over here. Basically, the point arises that what about finite finite wire? Word or not? So write it. We can write. We cannot derive magnetic field due to finite wire. We'll talk about that why and all. Write it. I cannot derive magnetic field due to finite wire by Ampere's law. Right or not? So, the question arises why? Because if we take circular Amperian loop, then what happens? We can see that what actually happens is, see, B needs to be always, if I take, if it is a finite wire and you took it, and you consider the circular Amperian loop, okay. So basically we know that magnetic field is tangential to loop or not. Now, so let's see, as we know that B of wire is tangential to the loop, isn't it? So basically this will be written as B of magnetic field due to wire dot dl vector. Are you able to get me? So this is simply B due to wire dot dl, isn't it? Now, second point is we know that B of wire have same magnitude at all point, isn't it? Then only you are able to write that integral B of wire dot dl is exactly equal to B into B of wire into 2 pi r. This is what we did earlier, isn't it? Magnetic field was same and dl was considered, and magnetic field is tangential to the loop. Are you able to get me or not? Now, this implies one of the most important factor that in our Ampere's law, when we select such closed loops to find B, which is equal to mu naught into I enclosed, Basically, these magnetic fields is due to everything on object. Got it or not? Are you able to get me? And see everything. See here, as I considered the wire, so current I is going and all. Are you able to get me or not? So now, when these currents are going up and down or something like that, okay. Now, if you consider every part, does the current is always going upwards only? Is there is no resistance in the wire? If there is some resistance in the wire or not, that such some of little bit. I'm not talking about maximum or minimum. I'm talking about that fraction of current which is lost here and there. Are you able to get me or not? So if we consider Ampere's law, then B is due to every such currents. Are you able to get me or not? Ha. And we cannot ignore current going in and out of wires because they are at finite distance. So see that what happens that when we apply a pure Ampere's law, then because we are calculating this magnetic field at such a point which is at a finite distance from wire, all these currents, whether it is going up or going down inside that loop, will be considered. Are you able to get me or not? So that's what I'm saying. B is calculated due to every part of current. Are you able to get me or not? Whether it is going up, down, or whatever it is. So at point P, if you want to determine B according to Ampere's law, it will not say whether the current is going up or down. You have to include both of them. Are you able to get me or not? So when I take the finite wire, what happens? We cannot derive such magnetic fields because we do not know in really infinite wire where my current is spreaded, where my current is fixed, where my current is stopped. Are you able to get me or not? But for infinite wire, total current can be easily considered. Are you able to get me? Because no such thing, no such length thing will come into the mind. Are you able to get me or not? So this is why magnetic fields are not applied for the case of which case? For finite wires. Okay. Yes. Are you able to get me? Good. Okay. Now look over here. So this was the thing due to a finite wires. Give the heading. So Srishti, I was asking one thing. Your vacation is started or what? When? Yesterday. So today onwards vacation started. So you schedule other classes always. See, you leave my two timetables. Okay. First thing is between 7 to 11 you leave for physics, and 9:30 or 10 to 11, 11:30, 10 to 12 we can say. Leave two schedules for Anurag sir. Apart from that, tell any other teachers to take the classes. Okay. Will be there. They will be able to take. Yes. Yeah. Okay. So let's. If I will take class, I'll take from. Okay. I'll take from 8:30 to 10. Okay. So these two schedules, you leave it. Okay. Either out of these two, one I will take, or some days two also I'll take. Okay. No, no, this is AM one and this is PM one. Morning schedule, evening schedule. Okay. Uh, Done. Okay. So you just keep this. These two schedules are fixed. Okay. Today, if I'll be comfortable, I'll take the evening class also. Okay. And in evening class, today, let us start our 11th class. Today is which day? 29. When is your next test? 7th July now. Okay, then capacitance will for Allen test and electrostats and all those things are coming now. Yeah, I have seen it. I have seen it. You just share me once yours also. Just remind me also because I forget now. Okay. So you just remind me which chapters are there. I'll share some more DPPs regarding that. Okay. Last DPPs. Okay. Yeah. Next thing, what I was saying. Okay. So today, let us start. See, morning one will go with this particular schedule of normal classes. If today I'll have time, I'll start with thermal physics. Is that fine? Thermodynamics. Which thing will come fast? Means thermodynamics will come fast, or rotational or center of mass will come fast? Which thing I should start? Tell me. Rotation is there first. So let us start with center of mass and collision. Till collision we have done now. So center of mass and rotational motion will start today. Okay. So infinite, we will complete this. This month we'll have to put some extra classes and do everything fast. Okay. So give the heading infinite long current carrying hollow cylinder, and that is pipe. So this time I have an infinitely long hollow cylinder, which is like a pipe. Go ahead or not? And I want to find the magnetic field into it. Okay. Now I want you to find. Shit, what has happened? Now look over here. This is a cylindrical wire. Okay. Now the current is moving on the surface. Okay. Current is going from where? This surface is. This surface. Because it is a hollow cylinder. Are you able to get me or not? So current is not present inside the region. It is present from the surface part. Are you able to get me? And I want to find the magnetic field. So let's suppose if I want to find the magnetic field first. Let's suppose let us consider one axis of the cylinder. This is my axis of the cylinder. Okay. And I want to find the magnetic field at some point P over here. So first thing, outside we'll consider, as we can have three different consideration: point P outside, then on surface, then inside, then on the axis. Are you able to get me or not? So look over here. So B, if I want to find, then I can directly apply simple Ampere's law or not. Yes. So basically, what it will be? First thing, first case. See, if I can apply here, then charge in current enclosed is total current I or not. So mu naught I, and if you this is radius r. If you consider Ampere law, it is length as 2 pi r. Are you able to get me? So for this is for r greater than r, if the radius of the cylinder is capital R, which is outside, isn't it? You only see me. If I consider a loop over here like this way, it has length how much? 2 pi r. So mu why or not? That's why I'm not writing it, not deriving it. Are you able to get me? Second thing, if I come on surface, then it is same mu naught I by 2 pi capital R. R is equal to R, that is on surface. When you select a point P inside it, let's suppose if I selected a point P over here, when I create the empirical loop, is I'm considering is there any enclosed current over here? I is equal to how much? 0. So basically this is how much? 0. For R less than R inside. When you consider axis, it is 0 because R less than R, nothing is there. Are you able to get me? There is no current inside. Is that clear? So when we draw the magnetic field variation with respect to distance r, then see that this is r equal to r until over here there is okay till over here there is no magnetic field is present till the surface of the cylinder, no magnetic field. After that, magnetic field suddenly becomes maximum and it starts to decrease in a linear way. Is that clear? So this is b one b inversely proportional to 1 by r, and this point is r is equal to capital R. Is that clear? Got it? And this maximum value is how much? Mu naught I by 2 pi capital R. From here it starts to decrease. Is that clear? Can I move ahead? Okay. So you got all your point. Next thing is, let us consider next one, which is magnetic field, and I have this time infinitely long current carrying solid cylinder. Okay. And see, Srishti, if there will be no today evening class, then I'll inform you. Okay. So, but tomorrow, tomorrow there is fixed, means 8:30 to 10 a.m. is fixed. Why don't? Pakka, pakka, pakka. That is totally fixed. Got it? If there will be any change in schedule due to my classes and all, then I'll definitely tell you. Okay. Now I have this time which kind of a cylinder? Solid cylinder. Got it? Perfect. Isn't it? Now consider some kind of a current is passing through all of this. So if a current will pass, you only say me, the current will pass from here, from here, from here. Everywhere the current will pass or not, isn't it? So basically, I'm not considering that. I'm considering that current is present at all surface and I'm writing it directly I. So I is spreaded along the full surface
Yes.
of the cylinder. Are you able to get me?
Yes.
So let us consider the first case, which is outside. If I want to find the magnetic field outside the cylinder, got it?
Yeah.
So let's suppose when I consider outside the cylinder, point P, which is a small r, and the radius of the cylinder considered to be capital R. So then the magnetic field outside is what? Simple integral B dot dr, sorry, dl is equal to mu naught I. So total I will be enclosed or not? If I consider an empirical loop over here, are you able to get me or not?
Yes. Yes.
So once again, B is equal to mu naught I by 2 pi.
2 pi r.
Is that clear or not?
Okay.
Totally. Second
Yes.
case is on surface. Answer will be still same. B will be equal to mu
Yeah. Due
naught
to
I
capital R.
by 2 pi capital R, because R changes to capital R. But the third
Yeah.
case, which I consider it for inside, where R is less than capital R, there the problem will arise, isn't it?
Yeah.
See, when
Actually.
I'm considering the inside part, look over here. When I'm considering any inside part,
Yeah.
yes, it's- this will be like of an inside part or not. Let's suppose I want to find the magnetic field over here. Okay,
Okay.
so inside part will be like this region. I
Yeah.
have to consider this region. See, because the radius over here for this inside part is this r, the small r. Are you able to get me? So
Yeah.
I need to understand that how much current is enclosed in this inside region or not. Tell
Yeah.
me yes or no. I need to find that
Yes.
how much current is enclosed within this inside region. Are you able to get me? So for inside part, the first task is itself finding the current inside. So to find the current inside, current enclosed, okay, we follow the principle of current density. What we follow?
Current density.
Remember that current only spreads through area, not through volume. Are you able to get me or not? So
Yeah.
J is equal to, for total current I, the total area is how much? Pi r, capital pi r square. So for a
Yes.
small region, it will be what? I by pi, a small r square, pi cancel. I enclosed. So therefore, I enclosed in the small region is I into small r square by capital R square. Is that clear?
Yeah.
Clear or not? So look
Yes.
over here. If I want to find the magnetic field inside it, so magnetic field inside dot dl vector or on the curve on the loop is mu naught I enclosed. So B inside it is how much? Mu naught I enclosed is I r square by capital R square. And integral dl means once again 2 pi r or not? 2 pi into
Yeah.
small r. Small r cancel. So B at inside point is how much? Mu naught I r by 2 pi capital R square. Is that clear? So you can see
Yeah.
here. magnetic field varies outside inversely proportional to 1 by r, but inside
Yeah.
it is directly proportional to r.
Yeah.
So when I draw the diagram, the diagram will be like this. First, it will increase linearly,
And then it will decrease.
and then it will here be it is inside for r
Yeah.
less than r. This point is r less than r, and this point is r equal to r. From here, it starts to decrease faster.
From R more than R, it will start decreasing.
Yeah. So B inversely proportional to 1 by r. So this is r greater than r. Are you able to get me or not?
Yeah.
So let's draw the conclusion. B is equal to, okay, first mu naught I by 2 pi r for r greater than r, mu naught I by 2 pi capital R for r is equal to capital R, isn't it? And mu naught
Yeah.
I r by 2 pi r square for r less than capital R. Is that clear?
Yes,
And
yes,
still
I think that is.
my B is equal to 0 at axis. Is that clear or not?
Yes.
Write it fast.
Okay, done.
Done? Can I move ahead?
Yeah. Yes.
Okay. So do one question. Let's suppose got the idea.
Yeah. Yes.
So basically, I have a hollow cylinder, got it or not? Where
Yeah.
inner radius is R1, outer radius is R2. Let's draw a
Yes.
axis. Clear?
Yeah.
So inner radius is R1, outer radius is R2.
All right.
Question is very, very simple. That the hollow cylinder, what is happening? The hollow cylinder carries current I. Okay. Then
Yes.
find magnetic field at point P in first case when R is greater than R2. Second case R is less than R1. And third case when R lies between R1 and R2. Do it.
Yeah.
What is?
R
A
is
small r is the distance of point.
horizontal.
Tell me what will be the answer.
Yeah.
Okay, see, I'm telling you an idea how to handle it. Whatever is figure given to you, okay,
Yeah.
I'll use circular. If this will be the visible cross section or not. If it is a
Yeah.
solid cylinder, I take out some part of it. Then this is my cross section, which is of hollow cylinder or not.
Yeah.
That the amount of reason means current is only present between R1 and R2, isn't it?
Yes.
So this is R1, and I'm considering the current coming out of it. So current direction is I like this way. Are you able to get me? This is
Acha.
R1. Yeah, basically do like that. Do always draw a 2D diagram. You can't solve in 3D easily. So R1, 1 minute. This is capital R1. This is capital R2. First point I have to consider a region which is present outside, isn't it?
Yeah.
So in first case, magnetic field dot dr, if I apply, is equal to mu naught I. So total current it will enclose, isn't it? So B
Yeah.
is equal to simply mu naught I by 2 pi r. If this point P lies at a distance of r from the center.
Yes.
Second case, when you consider a point P inside it, you only see. If I consider any empirical loop over here, any kind of current is not enclosed.
Zero.
So B is 0 for inside case. Third case is left. Third case is I have to check for that part, okay, which lies in between it. This is point P. Right or not? So when I
Yeah.
select a empirical loop over here, some part of the current from that surface is outside while some part lies inside, isn't it? So I have to find the current here or not, that how much part of the current is enclosed within this region. Are you able to get me?
Yes.
That this enclosed region is like this way only. This is my I enclosed region. Are you able to get me?
Yes.
When I consider the in between point. So look over here. How to find it? Simple. I told you already use current density formation. So current density for bigger is I by pi capital R2 square minus pi R1 square, isn't it?
Yeah.
I, because whole circle is not there. So pi R2 square minus R1 square. That's my current density here. For a small one, it will be same. So I by
R2 square minus R.
is equal to, in R1 square there is no current density also. So I enclosed, this time it is pi, simple, uh, small r square minus R1 square, because in R1 square region there is no current density. Are you able to get me or not?
In R1 square there is no current.
Yeah, here it is
Yeah, yeah.
vacant space or not. So I enclosed is I r square minus R1 square divided by R2 square minus R1 square. Is that clear?
Yes.
Totally.
Yes.
So write the now magnetic field equation. Basically integral B dot dl for enclosed region, between that is mu naught I enclosed. So B into 2 pi r is equal to I capital small r square r1 square by r2 square minus r1 square. So this is equal to, therefore B in between region r1 r2, it is equal to I by 2 pi r r square minus r1 square by r2 square, sorry, minus r1 square. Is that clear?
Yes.
That's your answer. Hey, I forgot one term. Where is my mu naught? Here it should be mu naught.
Mu naught. Not I.
Clear?
Yeah.
Okay.
Yes.
So next, I'll give you one question as a homework, which we'll discuss tomorrow or today, tomorrow.
Tomorrow.
So it is saying that current density of any particle or in a wire varies with R as J is equal to J naught R to the power of n. Okay,
Yeah.
is that clear? Then find
Yes.
first, first current I in the wire. Second, B for magnetic field for R less than capital R. Okay.
Yeah.
Second question saying a cylindrical long cavity of R less than capital R is made inside current carrying wire. Current carrying, not solid cylinder, you write. Current carrying solid cylinder. This cavity is parallel to the axis of cylinder. Got it?
Yeah.
Prove that magnetic field inside the cavity is uniform. Okay?
Okay.
So two questions only, which we will try and show me if it is correct or not. And then I'll solve your doubts and I'll share it. Okay?